at the effects of snow and ice contamination on aircraft performance and control. Your learning objectives for this lesson are listed here. It's important to appreciate how and by how much ice and snow can affect your aircraft performance and control ability. So, for ease of understanding, we have separated the effects of contamination in three categories. The effect of airframe contamination on performance and control. The mechanical effect of aircraft contamination and in-flight icing conditions, and the effect of runway contamination on performance. All the performance and safety calculations produced by your aircraft manufacturer are based on the assumption that the aircraft is clean. To put it another way, none of your performance calculations will be valid if your aircraft's critical surfaces are contaminated. So, in Part 1, to emphasize this point, we will look at how quickly and by how much even small amounts of airframe contamination can degrade performance. Airframe icing is a serious hazard and has an adverse effect on all four forces acting on the aircraft. Degraded aerodynamics and reduced thrusts, combined with increased weight and increased drag, can lead at best to reduced safety margins and at worst to dangerous handling characteristics. Look at some of the effects in more detail. The vast majority of lift is produced where airflow over the upper surface of the wing is laminar and attached laminar flow breaks down when the air in the boundary layer begins to lose its energy. When this happens, it loses speed and becomes turbulent. The boundary layer thickens and eventually flow separates from the upper surface. Beyond the separation point, the wing generates little lift on clean wing. The designer ensures that separation occurs predictably and progressively. The story is very different if the wing is contaminated with ice. The increased surface roughness quickly dissipates the energy in the boundary layer, leading to earlier separation and loss of lift. Most critically, separation is no longer controlled and progressive. It will occur at the lower angle of attack and may happen very suddenly. The key point to understand is just how little surface roughness is needed to disrupt the laminar barrier layer. The layer is only a few millimeters thick, so even a very small amount of frost or ice will have a very large effect on the ability of the wing to generate lift. Tests have shown that surface roughness equivalent to fine-grade sandpaper or wing walkway is enough to produce a significant degradation of lift. The graph here represents and is a result of practical flight trials carried out by Boeing using wing walkway paint to simulate frost. Notice the reduction in overall lift. The reduction in stalling angle and further reduction of both its slats are unavailable. In the latter situation, there will be no stall warning because the critical angle is now below the angle of attack that triggers the warning. Boeing also found that simulated frost on the slopes alone cause almost the same effect as contamination over the entire upper wing surface. By contrast, roughness on the lower wing surface produce only small effects. Unlike the wing, Both surfaces of the horizontal and vertical stabilizers can suffer serious degradation. This is because either surface is used to generate an aerodynamic force depending on the angle of attack. For this reason, both surfaces that the stabilizers must be kept completely clear of all contaminations. Ice contamination also has an adverse effect on drag. Firstly, the surface roughness of the ice will increase skin friction. Secondly, the reduction in lift caused by ice will require a higher angle of attack to lift the weight. This increases lift-dependent drag. The effect of frost contamination on drag may relatively be modest, but we will see later in this lesson that other types of icing can cause a huge increase. As well as reducing lift and increasing drag, ice also affects the other side of the equation. Ice accretion in the intake and on the fan propeller blades will reduce air mass flow and aerodynamic efficiency. This reduces thrust and gives you less margin to counteract the increase in drag. Similarly, the weight of the ice accumulating on the airframe will add to the problems already caused by loss of lift. Frost on the upper wing surface will cause an increase in stalling speed, a reduction in stalling angle by up to 3 degrees, and a reduction in lift of up to 30%. Drag and, to some extent, weight will increase, so the overall effect will be marked reduction in performance. In extreme cases, you may not be able to climb out of ground effect, or you may stall on rotation. Asymmetric icing is particularly dangerous and may cause uncontrollable yaw immediately after takeoff. We've seen the effects of a relatively thin layer of frost. So now let's look at two other forms of icing that can occur in the air: rime ice and clear ice. Rime ice is rough, white, opaque, and low density. It tends to form on the leading edges, and being rough produces effects like frost contamination. Clear ice is smooth, translucent, and relatively dense. It is altogether more serious a problem because it can accrete rapidly and add significant weight. These pictures from NASA show what can happen to a tailplane leading edge in light to moderate clear ice conditions. This diagram shows the increase in drag caused by clear and rime ice on a mixture of them, both on aircraft using no anti-ice protection in light to moderate icing conditions. It should leave no doubt about the scale of performance loss caused by ice contamination. The most severe form of clear icing is rain ice. Rain ice can accumulate very quickly and over a large area. It can take as little as 2 to 3 minutes of accumulation to increase drag by up to 100%, reduce maximum lift by up to 30%, reduce the critical angle of attack by 8 degrees, and substantially increase stalling speed. Under such conditions, ice protection systems may be overwhelmed. So not surprisingly, no aircraft is cleared to fly in known severe rain ice conditions. Accumulation of ice can also affect the aircraft's handling characteristics even before any degradation in performance becomes apparent. Disruption of the airflow over the ailerons can reduce their balance and cause uncommanded roll. Pitch upsets may also occur if the surface of the horizontal stabilizer becomes contaminated. In most commercial aircraft, The four forces arrange to produce a small pitch down movement, which is normally counterbalanced by down force produced by the horizontal stabilizer. Ice contamination on the stabilizer's lower surface can provoke early separation, leading to the loss of downward force and ensuing uncommand pitch down. This effect almost is always aggravated by lowering flaps, because flaps increase downwash, which increases the stabilizer's angle of attack. This leads to an earlier onset of the stall. On aircraft fitted with elevators, the disruption of airflow can also reduce elevator effectiveness or induce uncommanded or uncommon oscillations. In Part 1, we looked at the aerodynamic effects of contamination as well as disrupting airflow. Ice contamination can also have direct mechanical effects on the aircraft's controls and sensors. And other in-flight icing conditions, particularly hail, can have serious consequences for the safety of your aircraft. Mechanical effects. We mean any physical interference with the aircraft rather than effects caused by aerodynamic factors. These can be a common problem in winter operations. Mechanical effects can be divided into two categories: physical interference with controls and sensors, and physical damage to the airframe or engines. Physical interference may cause restricted or jammed controls, jammed landing gears, or other malfunctions such as frozen microswitches, static vents, AOA vanes, and other sensors may produce erroneous readings or cease to work altogether if they become contaminated. In-flight sensors are well protected by heaters from all but the most severe conditions, but control restrictions may occur when ice forms in hinges or around operating mechanisms. This can happen even when anti-icing systems are used because melted ice can run back and refreeze in an area beyond the reach of the anti-icing system. And as well, we shall see in a later lesson, control restrictions can occur when rehydrated anti-icing residue freezes. On the ground, sensors and controls may become contaminated either by ice or snow or by the consequences of careless or inappropriate de-icing and anti-icing. For example, control surfaces can become jammed if snow is brushed into the hinge areas, and sensors can become contaminated if de-icing fluid sprayed into their protected areas. Physical restrictions to the primary controls may be readily apparent when you conduct your full and free movement checks, but contamination of sensors can produce dangerous and insidious errors. The second category of mechanical effect covers damage from ice impact. Ice ingestion can cause engine flameout or damage engine vanes and blades. In extreme cases, the ice ingestion has caused catastrophic engine failure. Serious damage can occur to the airframe by impacts from large hail or from ice breaking off and hitting the rear surfaces. So far, we've considered the effects of contamination on the airframe. In this final part, we will look at how runway contamination can also affect your aircraft's performance. A runway is considered to be contaminated where more than 25% of the surface area is covered by standing water, slush, or loose snow with a water equivalent depth exceeding 3 millimeters, or when it is covered by compacted snow, ice, or wet ice. Contaminants on the runway will retard acceleration and ingested spray thrown up from the runway may reduce engine thrust. Either will result in an increased takeoff roll. Similarly, a lower decision speed may be required to take into account of the reduced braking efficiency in the event of an abort. Contamination can also affect directional control, so the crosswind limits are likely to be lower. Performance calculations must take account of the depth and type of contaminant, the braking action and associated crosswind limits, the use of engine anti-icing or any anti-icing fluid applied to the aircraft. Remember that the net takeoff flight path and the departure profile will be affected by any delayed gear retraction or gear recycling. On a contaminated runway also requires special consideration. The principal concern will be reduced braking performance. One of the main risks of landing on a contaminated surface is the risk of hydroplaning. There are three types of hydroplaning: viscous, dynamic, and reverted rubber. Viscous hydroplaning occurs frequently on wet runways and is caused by the normal lubrication effect of water. Although the water reduces friction, sufficient contact is made between the tire and the runway surface to allow the wheels to spin up and initiate the anti-skid system. Dynamic hydroplaning is the technical term for what we normally describe as hydroplaning or aquaplaning. In this case, the tire is completely lifted off the runway by the wedge of water. This can prevent the wheel from spinning up. Dynamic hydroplaning occurs most often on flooded runways. It is most likely if the runway surface has a poor micro texture or if the landing itself is particularly gentle. Reverted rubber hydroplaning can occur when a locked tire skids along a wet or icy runway long enough to generate significant heat. The heat generates steam, which lifts the tire off the runway and reverts the rubber to a gummy mass. The tire then floats on the liquefied rubber, reducing friction to that of an ice-covered runway. Poor surface friction can be caused by a layer of frost, by ice close to freezing point, or by covering of snow just below freezing point. In colder conditions, particularly where dry snow has been below -5 degrees for more than 24 hours, braking action can be acceptable. When brakes are applied, the tire is made to roll slower than its free rolling speed. The result is slip. Maximum braking is achieved in about 10% slip, but the available braking force depends on the vertical load on the tire. Therefore, any action that improves the vertical load as soon as possible after touchdown will enhance the available braking effort. Speed brakes, spoilers, and reverse thrust work most effectively at high speeds and are not affected by runway contamination.